Thank you everyone for joining us today for this exciting how-to session on preparing large data sets for analysis. My name is Meena Dalmata, and I'm a research and data analyst at Cooper-Smith. And I'm joined by my colleague, Michael Mashinsky, who I have the pleasure of working with. Michael leads the data science efforts at Cooper-Smith, designing and implementing systems that take advantage of the latest technologies and algorithms available for processing and understanding data, while ensuring that they are genuinely useful to those making decisions and that they adhere to the strictest ethical standards. He started his career at startups in the private sector, working as a chief software architect and chief technology officer at a company that created custom software for the aid sector. There, he designed large-scale applications for clients such as USAID, the UN, and IRC. Michael founded a startup that delivered data science and machine learning solutions to organizations in the nonprofit sector before joining Cooper-Smith. Today, Michael will be talking to us about an overview of the uses and abuses of large data sets and what tools and strategies to use to make them useful for your project. This was born out of his work supporting the government of Malawi to better respond to the COVID-19 pandemic. During this time, Cooper-Smith received access to anonymized call and message records from a leading mobile network operator. Thank you again, everyone, for joining, and Mike, a warm welcome. I'll turn it over to you to get us started. And just a reminder before you kick off that because this is a breakout session, people can turn on their microphones and videos to ask questions when we get to that point in the presentation. Thank you.
Thanks very much, Meena. That was super nice introduction. Yeah, basically, as Meena said, I'm the chief data scientist at Cooper-Smith. And during the COVID pandemic, we were able to gain access to a very large anonymized set of mobile call records, obviously with no demographic data, but nevertheless, getting this set into our systems and getting it into visualizations that were actually useful for the government and other responders to the COVID pandemic was quite a challenge, during which we learned a lot of lessons. So I sort of wanted to give you guys a general idea of some tips and tricks for working with big data, some of the more technical details, some of the software available, and generally an overview of what it's like to use these kinds of data sets in a global development context, be it pandemic response or other contexts for your projects. So just quickly, why is big data important? Well, big data has become a big thing over the last several years, largely because computing power has made it possible to do things with data that we weren't able to before. And it allows us to work on tens of millions or hundreds of millions or billions of rows in our case without having to create a model to approximate or aggregate them. We can literally process every single one of those millions of data points. And there are many algorithms these days in what gets called machine learning, such as some k-means algorithms, some gradient boosted algorithms that really work best when they have these huge data sets, not to mention, of course, neural networks and the like. Finally, in addition to the computing power, there has also been an emergence of service providers such as Amazon, Google, Microsoft that have really solved a lot of the hard problems around the infrastructure needed to work with big data and have made those solutions available to the public, not for free, obviously, but nevertheless, someone who does not have server management skills can run a big data project nowadays, and that's been a real game changer. I, for example, am a terrible server administrator, but that hasn't stopped me from working with this kind of data. However, as I go through the presentation, I also want to include a few caveats around the whole concept of big data, with capital letters. It's one of those terms, as I'm sure we all know, that gets tossed around a lot, similar to machine learning, artificial intelligence, that gets a lot of hype, but sometimes the hype isn't deserved, and sometimes the data just isn't that big. So I think it's really important as you come up to working with a big data project, ask whether you really need it, whether a smaller data set is able to accomplish the same thing as your much larger one is. And similarly, a lot of people use the phrase big data when the data just isn't that big. I mean, it's really incredible what even a personal computer can do these days. So, and there's nothing wrong with working with small data or medium data if you get the same result. There's no need to be putting buzzwords into your pitch or whatever. So broadly speaking, I'm going to focus on how to work with big data when you need it, but also try to keep an eye on when maybe you don't, and maybe when you can go with a cheaper or easier solution. Just as a quick shorthand for what I'll be doing, these are examples from our medical health data here in Malawi. Something like a facilities register that has 1,500 entries, I'd call that small data. You know, you throw it into your laptop, you throw it in Excel, everything runs quickly, all the algorithms you need. Something that's medium data, but may seem quite big, is electronic patient records. I'm working here in Malawi, and EMR records, if every single person had exactly one patient record, there would be 18 million entries. And that may seem like a lot, but actually my laptop can handle a database of that size just fine, and it can run all the basic calculations very well. So that's another situation where, yeah, maybe you'll need a server, but it doesn't really need that huge data infrastructure. Of course, if you're running more complex algorithms on 18 million entries, then maybe you do suddenly get into that big data range where you're deriving a lot of individual data points from those EMR records. But broadly speaking, a personal computer or your average work web server can easily handle something in the 1 millions or 10 millions range. Meanwhile, where we really get to big data is, for example, the mobile call records. Currently, our company is receiving, fully anonymized, approximately 2.5 to 3 million mobile call records every single day. Now we're at over 5 billion entries over the course of the last year or so. And so that truly is a staggering amount of data. And because we run real-time reports on it, it gets processed every single night in a way that needs to be ready for when users wake up in the morning. And this is the kind of data where you really need bespoke infrastructure. It needs to be in a server cluster, not a single server, and it needs to have everything that interacts with it, all the algorithms and all the hardware, designed in a way that is specific to that volume of data. And that's really a lot of what we'll be talking about during this presentation. So starting with the first thing is your big data storage infrastructure. You've got all this data, where do you put it? Now, the obvious answer is Amazon Cloud Services or Microsoft Azure or Google, I forget what it's called. But, like I said, those are companies that have done a lot of work and have a lot of very talented engineers who have solved a whole lot of problems that are very difficult to solve on your own, balancing loads, etc. And so if possible, you want to use cloud services such as those. They're relatively secure. I think they're very secure, in fact, depending on how you view their relationships to various governments. But in general, that's my preference for the first option when you are trying to store big data. A lot of the hard work has already been done for you. But it's important to ask yourself, again, can a simple MySQL or SQL server handle this data set? Even if it's 100 million rows, but it's only a few columns, it's only key value pairs, it's only numbers, sometimes MySQL can just handle it. And so it's really important to ask yourself if you really need to be procuring that entire cluster and everything that involves, when maybe you have a more medium data set and you can meet your aims while using more off-the-shelf software that can run on a non-specified computer. However, if you are moving to the real big data situation and you decide you do need that full infrastructure, in my personal opinion, Apache Hive and Apache Spark are excellent options. You can go with Amazon Redshift, leverages them as well. These are fairly easy go-tos. They're all set up. When we run it, I was running a database on MySQL. We moved the same data into Spark, and I could run the same essential SQL queries, and they ran seamlessly, even though they were running on 4 billion records across multiple computers. So Hive and Spark are excellent choices. The other big name products that are similar from Amazon or Microsoft are excellent as well. Of course, Hive and Spark are open source, so you won't be having to pay licensing fees. Now, if you're already in Amazon Web Services, you may want to go with Amazon's paid software. It's sort of part of the package. However, there are certain types of data, so non-anonymized data, medical data, other kinds of government data that maybe your data provider, such as a ministry, will not allow you to host at a third party. They say, you can work with this data, but we want you to keep it in country. We don't feel comfortable with this going to a third party company in another nation. And in those cases, Hive and Spark are what you want to go with because they're open source. You don't want to be paying licensing fees and there's big communities. that support them. Similarly, for Spark as an example, you can use SQL or SQL, depending on how you like to pronounce it. PySpark, if you're used to working with pandas in Python. Spark R, if you're used to working with R, which I am not, but I know many of my colleagues are. So they're really flexible. You can go at it with your language of choice. Of course, you have to learn how to optimize queries for this, but nevertheless, it's really become surprisingly user-friendly, and a lot of the software has gone a long way to mimicking how the non-big data versions of this software works. And finally, it's really worth noting that even for Amazon or Microsoft cloud servers, you do need somebody to manage them. You do need somebody who's reasonably good at maintaining servers, who can tell when something's going wrong, who, if your CPU suddenly gets maxed out and you can't run any queries, can go in and figure out what might be happening. I, for example, am relatively poor at that, but I luckily have a brilliant colleague named Samer, who is a genius with this sort of thing. And without him, this would not have, the project that we did with the mobile data would not have been possible. So if you are looking to do your own big data projects on your own big data server instance, I really stress that you may need some expertise around server management. That expertise should already be present in your institution, be it an organization, a company, or university, because you will be managing some sorts of servers if you're a largish organization. But nevertheless, they do tend to require server administrators to run at their optimum. If you are forced to create a server cloud of your own in country, that requires really specialized staff, and you'll need to hire, network engineers, general hardware engineers that can do that kind of work and set up that system so it runs smoothly and flawlessly without overloading or constantly crashing. So just to give you some examples of data that can be extremely computationally intensive. So one example, obviously, is GIS data. And GIS data isn't big data because of its, quantity. Usually you'll have a few hundred or a few thousand records, maybe 10 or 100,000. But by and large, the problem with it is that it's very expensive to process, especially if you're working with polygons. Like if you're working with all the counties of the United States, well, a lot of them are going to have weird shapes, and there's going to be a lot of them. So to define a squiggly line that is a river boundary of a county, then that's going to take a lot of space to store, even though it's technically only one data point, because the polygons store every single point all along the line that you might need to process. And so already here, you might be getting into a situation where you need a larger data set or you need a larger data environment. However, it is genuinely worthwhile because, as I always say, people love maps. Anytime you present something and there's a map on it, generally you will get a good reaction. So you have to be really careful about your geospatial operations, but it's something that's really worthwhile for visualization. Similarly, something that easily gets into very large data sizes are GIS raster files. And so these are they're processed with completely different libraries than the shape files are, which is somewhat frustrating. But here the idea is that you represent terrain as pixels. And as you can imagine, that gets quite large. When you have a density map of a country like Malawi, where which data point is a square kilometer, where you're easily getting to the 100,000s of square kilometers. If you get a higher resolution, you got millions and millions of kilometers. And this is another case where one of the smart things to do when you're working with large data sets is try to keep it in its original file format for as long as possible. A lot of people are tempted to convert these pixel files into shape files, but then each pixel becomes a geometric square and you're massively increasing your overhead. And so it's really important to always be aware of how your data is stored and keep it small when necessary. And similarly, for example, on the subject of GIS data, you would have satellite imagery, which is orders of magnitude larger than raster or shape files. There, even if you're working with 100 photos, you're already in the big data range where it can't be processed by a single computer. So it's really important to process those as quickly as possible and then get them to a data format that takes up less space and less computation. Now, to give you the specific example of mobile call records, as you can see, they're really simple. This is not an extremely complicated format of data. It really is just 6 text fields. You have a phone number. Actually, we don't really have the phone numbers. Obviously, they give us a fake identifier because we don't want to be tracking anybody. But in theory, if you're the mobile network, you have a phone number. You have the time it happened. You have the name of the tower. You have something called a LAC ID, which if you're interested in mobile phone data, is sort of an area of towers between which subscribers switch. You have the type. Is it a voice call? Is it an SMS? And is it incoming or outgoing? And really those first three, or if you want to be more specific, first four, are what you need. So each individual data point, it's 4 Excel columns easily. 3 of them are numeric. It's not a lot to store. The reason it's important is because of the volume that you get every single day. We're getting 2.5 million records every single day into our system, and that needs to be processed. And even if each one was just a single number, well, processing it in a way that then becomes usable, and that means taking the GIS data I just talked about, coordinating it or correlating it with the mobile data and turning that into a usable form. Well, that's really the challenge behind using big data. And so one of the key things with big data is that these simple data points, once they get large enough, can really grow out of hand and become something that requires specialized software or specialized algorithms to work with. And the way we manage to work with these, I've sort of condensed into a series of data strategies. And one of the examples is always work with the smallest amount of data you need. And so, as we know, when we're working with data science, when we're working with new algorithms, the first thing we do is always take all the data, run a regression, see if it just works and we don't have to do anything else. But that's something you can't do with 4 billion rows. But it is something you can do with 100,000 or 1 million rows. And what often happens is, it turns out that a much smaller amount of your data actually can get you to the place that you want to be. Obviously, you have to be very careful about sampling and which data you're using when you make the data set go from larger to smaller. But in our case, we have over a year's worth of mobile records now. And one of our primary use cases is to use that to predict population density in a given place, i.e. if there's more cell phone users, we think there'll be more people in general. And we've done some small studies to prove that the correlation exists. However, you don't need to take that entire year to make that work. A single day, it's actually a pretty good approximation. Once you get up to a week or even 2 weeks, you're getting a result almost as good as the full year's worth of data, but you're only using 20 million, 30 million records instead of 5 billion records. And needless to say, computationally, that makes a world of difference. So it's always worthwhile to check whether a smaller amount of data gets you where you need to be, and if you really need to be devoting the computer time and the hardware storage time to everything, to the entire data set, even though the temptation, the easiest thing is always throw the whole thing in, see what happens. So that's why you want to check if a sample has similar results to the whole data set. That's how you get your smallest amount of data that you need. Try it on a single day of cell phone records. Try it on a week, try it on a month. Obviously, maybe you're doing migration over 6 months between the winter and the summer, or the rainy and dry season, as the case may be. But again, maybe you just need a month in the summer and a month in the winter. Maybe you don't need the whole thing. Another key thing is to keep your algorithm simple if you can. And the idea here is that it's always tempting to use the flashy new algorithms, your XGBoosts, everything that takes extremely, throw things into a neural network, et cetera, get your TensorFlow going. But often you get similar, if not quite as good results. Sometimes you genuinely get better results with a simple algorithm. So it's always worthwhile to try those first, because the cost of working with big data is the size of the data multiplied by the complexity of what you're trying to do with it. And I think that's a particular case where it's always worth it to try the simple algorithm. And especially as you're doing your exploratory phase, sometimes, if your exploratory algorithm takes an hour to run, you're not going to iterate as quickly as if you're using one that takes 2 minutes. And once you do find a complex algorithm, maybe it's not the more complex algorithm, maybe it's feature selection that helped you do it. So always with big data, you want to be thinking about how little to have to interact with the bigness of the data as possible. And in many ways, the most important element of this in terms of preparing your data sets is caching whenever possible. So as I described yesterday, does it feel like I've been speaking for that long? As I described at the beginning of my presentation, it's really important to cache wherever possible, because in our case, we have 5 billion records coming, 2.5 million records a day, and we're producing dashboards that are ready at 9 a.m. showing you what the movements have been on that day. Based on the cell phone records. This is as close to real time as you can get, really, with mobile operators feeding you data on a daily basis, once a day in the middle of the night. And to make that possible, the dashboard, which is what the users see, it can't read all 5 billion records and tell you what's going on. It would simply crash. Like, even processing that whole 5 billion from scratch now would take hours and hours and hours, even on our large cluster. What we do is every day that it comes in, we take the 2.5 million records and we condense them down. First, we condense them to clusters of cell phone towers and assign each one a population. Then we take those clusters of cell phone towers and see how people move between them and assign them scores on how connected the clusters are and build out a network that way. And then we take the particular day of interest, which is usually yesterday from the point of view of our users, and we say, okay, on that particular day, what was the interchange score? How did it change from a week ago or a month ago in terms of population density? And really, once you get to your visualization stage, it's only working with, the 700 records that represent the sub-districts of your country or the particular cell phone towers. And this is a crucial strategy. Our algorithm essentially is 5 steps of caching, each one smaller and easier to process than the last, until your Python script at the end, or your R script, or your dashboard works with something that's really manageable. And that's how you create routine big data. It's obviously easier if you're just writing a report to just send it running for 3 days and publish the output. But if you're creating something that needs to work on a day-to-day basis, that's often not possible. So caching, making sure you have an algorithm that can take a subset of the data and add it to another process subset without losing the data integrity, that's a really crucial element of the entire strategy. And finally, one thing I always warn about that can A, cost you huge computing resources, and B, actually make your results worse rather than better, is what I call artificial specificity. One example is we have a data set of Malawi, that's a raster set. It's at the 1 square kilometer level. The entire country divided into square kilometers with some data on each. Now that set is available also at 100 meter by 100 meter resolution. There's a question about whether that particular data set is really, like, did they have the methodology to really go down to that 100 meter level? Because that is extraordinary specific. That's, a block or 2 at most. And second of all, do you really need it? One of the things we were doing was creating an algorithm to place potential health facilities in places where they would reach the most people who aren't yet covered by other facilities. The government can't build something on a specific 100 meters square you indicate. They can build something in the general area. Even a square kilometer can already be larger than the potential construction sites in an area. You can't just plop something down wherever you like because a computer told you to. And that's a case where using the 100 meter by 100 meter data set would make the computation more complicated by an order of magnitude, while making something arguably less useful and less clear on whether it's working or not. So it's really important to say, hey, do I need something at this resolution? Do I need something that drills down to this, or am I washing away that resolution anyway with some of my algorithms, and I could have just used, the smaller and more manageable one. Finally, a subject I wanted to talk about that it's not exactly preparing data sets, but it's a really crucial element. And I think it is a very crucial element into making big data useful in a way that will get, future projects funded, but also in general, give you something that users can use or decision makers can use, or even, other academics can read. And that's data visualization. When you have 5 billion rows, it's a challenge to put them into a small dashboard that goes on a single screen. Now, there are multiple choices in terms of your visualization strategy. Some of the most obvious are paid products like Tableau and Power BI there. fast, they're beautiful, they look great. The second you put something in them, it looks extremely professional, as you'd expect from a product of a large corporation. Of course, the big drawback, they're not free. They have to be paid for. I do believe that they are generally worth the money that you paid for them. And they also tend to struggle with flexibility sometimes. Sometimes they can do almost everything like magic, and sometimes you want to change one small thing and suddenly it's impossible. So we believe they are really excellent tools, but they're not always the ones for every single use case. However, the alternative generally is making your own custom dashboards. This would be in R or in Python. I use the example of dashboards because I primarily work in routine data, but obviously these can be visualizations that are meant to be published. And these tend to be much more work intensive. You need programmers who are proficient in ggplot or in Python or in a web-based framework like Plotly if you're going to make these work. And sometimes, whereas with Tableau and Power BI, if you get your data down to a manageable level where the software can process it, and it can actually process pretty large amounts of data, then your non-technical staff, and by non-technical I mean non-programmer, apologies, your non-computer programmer staff is capable of working with it. So each comes with its own pros and cons, and at our company we literally use both. Every time we have a project, we're like, all right, should we do this in Tableau or should we do this custom in Python? A crucial thing, as I mentioned earlier, is to always visualize the smallest possible data set. Visualization code is expensive generally. Obviously, the libraries try to do some of that for you, but you don't want to feed a million rows into a graph just so it can produce one line where the visualization library does all the averaging for you. Basically, you want to calculate that yourself, and especially if you're working with big data, you have to do it yourself. And so what you want to do is when you feed data into visualization, you should feed only the exact data points that visualization needs. Now, obviously, if you're visualizing something like error bars or uncertainty, you might need every data point because it's the graphic algorithm itself that determines how those bars look. But in general, if you're doing a bar chart, if you're doing a line, reduce the data yourself. You have to in the case of big data, and then visualize that. And finally, something that I think is important, and this comes in, I'm talking about this in the sense of visualization, but this is important even when you're preparing your data set at the very beginning by deciding what data points to include. And it's about understanding who's going to be viewing the data visualization or the data output. Maybe if it's an academic peer review, then you need as much in there as possible to prove that your thesis is correct or that your results are valid. But if it's something for a government user or a manager or a non-technical decision maker of some kind, you really want to understand what they're trying to do and optimize for clarity. Optimizing for clarity, A, saves you time because it's often less computationally extensive, but B, really makes the data more useful. With the dashboards we produced using this M&O data, the hardest part was cutting down the dashboard. We had all this really cool data about where people were, where they were moving, but putting it all on the screen, all it really proved was we have a lot of cool data. Whereas what we wanted to do was, hey, this is information that you need to be able to do your job. And so we cut down and we cut down, we wound up with a dashboard that has only a few screens. And that's a really important element of working with data, is really cut it down, not just for computational reasons, not just to get it, working on a smaller computer or running faster, but also to only use the data you really need to output. Because users get overwhelmed very easily, and when you've seen all the data personally, you know how much is there and you want to show it all off. So it's really important to optimize for clarity. And as I said earlier, people love maps. That's why I put GIS software in there. It's one of the most effective ways of getting a large amount of data into a format that a user can understand, because most people that are working with your outputs will have a visualization, will already have a mental model in their head of their country or their city or their immediate vicinity or the world. And you can plug into that mental model with your data. And when you color it red or color it blue, it's much more effective than if you did a bar chart or a pie chart sometimes. Obviously, sometimes you need a vast variety of other visualizations, but maps are among my favorites. Finally, when you're deploying these solutions, and I'll wrap up quickly so we have time for questions, if you want data solutions to be routine, you want to design them to run repeatedly, like ours runs every day, instead of running once. And that means optimizing it so that it can be done over and over and over, and really paying attention to, maybe it works on 1 million rows, but let's make sure it will still work in 100 days on 100 million rows. You should do UX and UI design, understanding your users, and a user can just be a reader of a paper, depending on how you look at it, is super crucial. All the information you're including in your data solution should serve a purpose. I literally 2 days ago published, or showed my boss a visualization that had all the cool data we had, but it didn't really lead into any conclusions. It just said, hey, we have data. And so, I've had to cut it out because it just wasn't serving a purpose, even though it was there. And it's important to know whether your solution requires software and server maintenance or not, because essentially, as I mentioned earlier, software administrators may be necessary. All right, Zikomkwambiri, as we say here in Malawi, since that's where I've been working for the last year, I wanted to add a local flavor to it. But thank you very much, and I'm open to questions at the moment.
Thanks, Mike. Those were very helpful and practical tips on how to store, prepare, and analyze such large data sets. Just a reminder for everyone that you can request to have your camera and audio on to directly ask questions, or feel free to put them in the Q&A box that's to the right of the chat if you have any questions. I think just while we wait for people to prepare their questions, Mike, I'd like to ask about the data visuals. You talk about understanding your audience when visualizing such complex findings. How do you suggest that individuals who are doing this analysis decide on the best way to data?
Yeah, I mean, what we try to take is what's called a user-centric or a human-centric design approach. That is, again, one of those buzzwords that gets thrown down a lot these days. But in general, what you want to be doing is looking at the data from the point of view of the user, how they would see it without knowing all the sausage making that goes on in the background to get the data there. Obviously, the best way to do that is to talk to your potential users and to show them things. And then you get their perspective on it. If you're just working alone, you have to sort of try to divorce yourself from everything that you already know about what's happening and try to be like, all right, if I was just seeing this screen and I didn't already know absolutely everything about it, what would I understand? What would be difficult to follow? And one of the most crucial things here is to get feedback from your users. Even if you ask them, they're not user interface designers, they might give you bad ideas. Even if you have a lot of experience, often you'll do something that you think will be crystal clear and you show it to somebody for the first time and they have no idea what's happening. So it's really, really crucial if you're deploying software rather than just writing a report, or honestly, even if you are writing a report, to show it to the people who are meant to read it and get their feedback, because sometimes that's the only way you'll find out whether your visualizations are having the impact that they need. So having that kind of engagement with the users, obviously I talk about users a lot, but they can be readers or other audiences. I think that really is the most crucial element of the visualizations and outputs that you design.
Thanks, that makes a lot of sense. Thanks, Mike, and thanks to all of our attendees. That was great.